group, and as you can probably tell, I am located in the Bay Area. I'm just going to jump right into it. Give you a quick overview of what I'm going to talk about today. I'm going to start with some context. Why is this topic important? How measure costs are used specifically in regulatory and program planning activities. Hopefully have a brief overview of the kind of the core data collection analysis challenges associated with estimating measure costs. From there, we'll provide an overview of how we addressed some of those challenges in a recent measure cost study we completed for the California Public Utilities Commission, and from there talk about our recommendations and lessons learned for the road ahead. I'm going to start with some quick definitions because semantics are important. We all commonly say cost, but what we're really talking about is prices, technology prices. We also use the term measure, singular. Typically, or often that actually involves a pair of technologies, one replacing the other. And we also tend to say measure cost, but what we really use in cost-effectiveness analysis is incremental measure costs, strictly due to energy efficiency improvement. So, we're going to say I use these terms interchangeably, but for the record, when we say cost, we mean prices. When we say measures, we mean technologies, and when we say measure costs, we usually mean incremental measure costs. So, that said, why is this topic important and relevant for today? In a nutshell, there's been probably over the past 15 years or so of movement in the United States towards regulatory frameworks that rely on ex-ante or deemed values of measure cost and savings. 36 states use some type of deemed cost and savings values in their regulatory proceedings. With that movement in regulatory structures, there's also been a growth in the amount of resources used to develop those values. I think 15, it might actually be up to 17 now, states have technical resource manuals that include some of these deemed values. The flip side is that most of that research has focused on ex-ante savings values, with very little research being dedicated to measure cost estimates. Only 3 TRMs that we're aware of actually contain primary estimates of ex-ante measure costs. Even in California, who's funded 5 measure cost studies since the 90s, the total investment in impact-related research is roughly 2 orders of magnitude higher than cost research over the history of the industry. What does this all mean is, in our assessment, the current body of knowledge about how to conduct these things is small and innovations have lagged, which is strange when you think about it, because measured costs are a pretty central player in pretty much everything that we do in the larger energy efficiency endeavor. So this diagram here in a convenient pyramid form is trying to illustrate this. At the bottom we have program design. Measure costs are used to determine incentive levels for deemed measures. You can even determine incentive levels for custom projects when their total payouts are capped by total project costs. Got to know those costs well. For portfolio and program cost effectiveness, it's literally half of the cost effectiveness equation. TRC, incremental cost, is almost half of the denominator. In jurisdictions where you have market transformation goals, the key metrics that you really want to track progress towards market transformation are prices and incremental costs over time. Without that, you're not really sure how much market transformation is really going on. And then at the top of the pyramid, we have IRP, or Integrated Resource Planning. And in that application, what you're really doing is trying to compare the marginal cost of energy efficiency against supply-side alternatives. So this is a way of showing how central measure cost estimates are in pretty much everything we do in the energy efficiency industry. Now, part of the reason why things have lagged to date is that, yes, some of the things that we deal with in measure cost studies are hard, both on data collection and analysis. In terms of data collection, we tried to boil it down to basically 3 kind of fundamental challenges. The first one is real simple. There's a lack of reliable cost data in the public domain. Prices are closely held, competitive information in many industries. And in that way, the true population of prices paid is largely unknowable. On top of that, the actors in supply chains vary widely across the universe of energy efficiency technology and products. You know, if we think about what goes in the typical utility portfolio, there's hundreds of technologies in there, and a lot of those supply chains and actors are different and come with different data access challenges. The second fundamental challenge is that, unlike impact studies, cost studies have to bridge the gap between generalized measures and actual products. And by that we mean, you know, for impact analysis, you can aggregate things according to energy performance criteria, and that's all you really need to do a proper impact analysis. So, you know, whether it's SEER, AFUE, energy factor, R value, U value, etc. For cost studies, you can't simplify things strictly on the energy performance criteria, because products and prices can vary a lot within, for example, a particular SEER bucket or a particular energy factor bucket. What that means really at the end of the day is that cost studies you need to have sample sizes in the hundreds or sometimes in the thousands. And then the third kind of fundamental challenge I've tried to cleverly characterize as, you know, today's measures versus tomorrow's measures versus somebody else's measures. Historically, because data access has been difficult, cost studies have tended to be kind of hyper-focused on very specific measure definitions, typically those that are used in current portfolio offerings. You know, the impact of that is that, you know, the shelf life of the estimate can be limited because, you know, measure definitions and program offerings change. It also limits the transferability of estimates to other jurisdictions, because again, you can have nuanced differences in, you know, in program eligibility or program specifications across jurisdictions. You know, when you think about that going forward, in today's environment, which is a little bit more dynamic than it used to be in the energy efficiency industry, what you really want at the end of the day are high degrees of flexibility and granularity. And by flexibility, we refer to the, you know, ability to produce estimates across a wide range of measure specifications without having to go back into the field and collect new data every time. By granularity, we mean the ability to go from very specific cost estimates up to more prototypical aggregate estimates using the same basic analytic framework of data sources and have that internal consistency. So you can think of going from specific program design all the way up through higher level resource planning. You know, ideally you'd like to have that using internally consistent values. So having kind of, you know, this table shows a snapshot of some of the more common data sources, and you know, I don't want people to really try to read everything on this chart, but you know, in the left column, you know, program data, direct installation, third-party implementer price lists, shelf surveys, manufacturer catalogs, market actor interviews, construction pricing books like RS Means, and then point of sales data. These are kind of the typical array of places that that we get data. They all have pros, they all have cons, they're all imperfect, and I'm going to just try to pick out some themes on the left-hand side, or on the right-hand side here. Absence of installation costs. You know, things like water heaters or heat pumps have installation costs that you need to account for in incremental cost accounting, and a lot of these sources just don't have them. Lack of sales volumes for measures that have a lot of price diversity that's not related to efficiency, say refrigerators or televisions. You need sales volumes to do a good incremental cost analysis, and a lot of these A lot of these sources just don't have them. Small sample size, I think that kind of speaks for itself. Down here at the bottom with construction pricing books like RS Means, these are widely used. They're pretty good. The construction industry uses them a lot. A lot of program utility folks will use them as a kind of default source for benchmarking prices and whatnot. Specific to incremental cost analysis, it's hard to use those types of sources because the equipment specifications often lack the energy performance criteria that determines eligible programs and products. Also at the bottom, at point of sales data. Now these are great. This is a great source. This point of sales data is collected by third-party marketing firms and resold. They're very rich data sets. They can be very large. They're actual prices paid. They have sales volume data. But the key caveat with point of sales data is that it's limited to mass market measures, so meaning stuff that's sold directly to customers. And even within there, the marketing firms have tended not to focus on energy efficiency equipment per se. So it's a very narrow availability of point of sales data. So on the analysis side, we've talked through some of the data collection challenges, but really the fun is only starting. There's a whole host of data analysis challenges that I'll try to rattle through here. The first one is incremental cost accounting at its most simplest form is match pair analysis, and part of that is the high efficiency product and the baseline product. And for some equipment, baseline is very easy to determine because it's regulated by code, like for a water heater or for a central air conditioner. For others, like televisions, it's the question of what is the baseline is a big question. Is it a CRT television? Is it an LED television? Is it a plasma television? Second kind of core data analysis challenge is trying to isolate price differences strictly due to efficiency. Refrigerators are an excellent example here, where you have price effect. You're trying to isolate the price effect of energy efficiency separately from the impact of whether it has a stainless steel finish or through-the-door ice. Another challenge has to do with life cycle costs. The total resource cost test and most business decision-making models like internal rate of return are actually life cycle cost tests. They're not first cost tests. And to do that, you need a whole bunch of other stuff that is also understudied in our industry: remaining useful life, O&M costs, salvage values, disposal costs. In the custom and new construction program world, you also have to deal with things like standard practice baselines for industrial process equipment, and sometimes interactions between building design choices and total building costs. And this, particularly in terms of equipment sizing, there can be significant interactions between lighting design and HVAC design, for example. Now, on top of that, there's a set of temporal dynamics related to incremental cost analysis that are becoming more and more relevant in the modern world. One is price forecasting. This chart shows the average price of the CFL A-lamp over an 8 or 9 year period. This is from Itron's residential market share tracking study. In principle, for any planning study, you would want to have technology prices forecasted forward, and then it brings up the question of how you do that. We know that in CFL is a good example of how dynamic that can be. I think LEDs are probably even more dynamic than the CFL market. On top of that, we have a baseline, a code baseline that is moving. This chart kind of summarizes the rulemaking outlook for the U.S. DOE, and you can see that these are a lot of types of equipment that are typical in IOU program portfolios: furnaces, room AC, central heat pumps, clothes dryers, and that baseline is moving and changing over the forecast horizon. On the flip side of that, these are the planned updates to the Energy Star label specification. These are also changing. So you have the baseline changing, and you have the measure definition changing. So kind of listening to all that, for us, there are really kind of three big questions that emerge from all these challenges that measured cost studies have faced historically. Are there really ways to get better data than what's been done in the past? Are there ways to increase the flexibility of these estimates and increase their shelf life and overall value? And and then bottom line, can we do this faster and for less money? And we believe that the answer is yes to all three. And hopefully we're going to use some describe some of the approaches that we used in this California study, hopefully to illustrate that for folks today. For some high-level parameters on the project that we did for the California PUC, it was a $2 million project that was roughly over a 3-year period. I got to give a shout out to my project manager, Katie Wu, and her supervisors, Jacqueline Marks and Carmen Best, who oversaw the larger EMV portfolio. We're very grateful that they had the foresight to make the investment in this particular research. We thought it was very critical. The scope of the project was quite large. It was larger than any cost study that's been attempted in California in the past, in that it included both DEER measures and non-DEER deemed measures. So it was a significant, large effort. So on the data collection side, for unit equipment prices, we basically had two strategies. For mass market measures, meaning anything that was sold directly to customers, we tried to assemble very large samples of actual retail prices, and then we leveraged as much point-of-sales data as was available. This is covering appliances, electronics, and residential lighting. The res lighting was supplemented by a large retail shelf survey effort that was done by another firm as part of a different evaluation that was going on. We got to leverage that. But for a good chunk of the portfolio, they're measures that they're not mass market measures. These are measures that are procured by third parties on behalf of customers. And for those, we used a retail price buildup approach. And the key part of that approach is that rather than trying to collect final prices, we collected price data at the distributor level and supplemented that by explicit markups, estimates, and things like that. This price buildup approach actually mirrors the method that contractors and ESCOs use to do project pricing estimates. A key part of the strategy is that we partnered with subcontractors who are in the supply chain in order to get at the distributor price list. And the key aspect of it is to leverage their existing relationships with distributors. Distributors are not willing to share data with people who call them out of the blue, but if you have an existing relationship, they're more than happy to provide their price list. So this is definitely a key aspect of our data collection approach that we thought was pretty successful. On the analysis side, we used hedonic price models wherever we could. Hedonic price models are basically a regression approach that allows you to isolate the relative influence of individual features on final price, and those features could be capacity, energy performance, color, brand, anything that you think influences price. The key advantage of hedonic price modeling, and the reason that we tried to implement this as much as we could, was that not only is it you can explicitly control for cost factors not related to efficiency, but perhaps even more importantly, we could estimate incremental costs really across a continuum of technology specs. So by nature, it had a high degree of flexibility and granularity in the approach. And then on top of that, we actually got empirical estimates of uncertainties in forms of standard errors and other statistical precision measures. So this next table, I'm not going to walk through all of this. This is just an example of one of our hedonic price models. This one's for refrigerators. On the left-hand side, that just shows you the variables that were included: capacity, door configuration, color. At the bottom is kWh consumption per year. On the right-hand side, shows you the sample sizes and the total model fit, 0.86, which is really good. And at the bottom, just the specific result for rated kWh per year. You can see the t-statistic is 5.2, indicating statistical significance. The coefficient is that is estimated by the model is minus 0.47, which is, that shows you a price premium for reductions in annual kWh, so a positive incremental cost. So how do we use all that craziness in this big table to actually predict prices? This is, again, using the refrigerator example. This is the formula, the basic model specification expressed as a formula. And if you look, we take simply the estimated coefficients from the models and interact those with the parameter inputs. And the parameter inputs in this case are, the key ones are Energy Star compliant, side mount freezer, through the door ice, 27 cubic foot total volume, and 620 kWh per year. And it's really this simple. After you've estimated the models, you can really just plug and play. This particular, the average price for this particular configuration is estimated to be around $1,000. You do the same thing for a baseline unit, take the difference between the two, there's your income all cost. So you can see how the flexibility is really quite obvious in this approach. As much as we wanted to do this across the board, we couldn't for several reasons. There are some measure groups like commercial refrigeration that are more like projects. They're not really specific technologies. HVAC maintenance can include a whole bunch of interventions. Think about refrigerant charging or any type of HVAC optimization. And for those, we used either built-up estimates done by specialized subcontractors or some type of simple average, either a match pair or a whole sample average. Now, on the labor side, we decided to kind of split the estimates of installation labor hours from the question of labor rates. And so to develop installation labor hour estimates, for most of the small HVAC and lighting, we used a very large contractor survey. We had very large sample frames in the tens of thousands, and we got roughly 100 completes each. And we did a telephone survey. We had a variety of installation scenarios. For some of the larger capital equipment, we used a set of artificial project bids where we actually spec'd out specific installation conditions, and sometimes we varied the installation scenarios to look at how installation costs might vary. For example, a rooftop installation for a package unit versus a ground installation, things like that. We supplemented those things with information from the direct installation contractors, as well as RS means and estimates from the DOE's technical support documents. And so that provided installation labor hours, and then we actually used the RS means values for the rates across the board. That allowed us to at least ensure a certain level of internal consistency, but it also allows us to customize the installation, the total installation costs to specific locations using the RS mean city cost indices. In total, through our effort, we produced estimates, measure cost estimates for 60 measure groups, and I think it all combined that with all the various kind of iterations of measure definitions in DEER, I think it accounts for over 600 individual measures, deemed measures in California. We also had about 92 different installation cost estimates covering 49 measure groups. We developed some installation cost estimates for stuff that is treated as replacement on burnout in the deemed world, but actually gets claimed as early replacement in the custom world. So we actually tried to build in some flexibility, applicability into the custom program. The link at the bottom for the final report. I'm going to skip to our recommendations. And we had really kind of three big recommendations, and these are all focused on actionable stuff that utilities can do in California to do better, cheaper, and more frequent cost studies, like for real. Now, the first one is seems somewhat inane, but this is big, and this applies to jurisdictions across the country. Integrating make, model, and cost installation cost data into program tracking. Make model data is usually required on rebate forms, but it's surprisingly not often pulled into program tracking, and so it's kind of lost along the way. Installation costs are hardly ever required on rebate forms, even if the unit requires necessarily a third-party installation. We believe that it would be feasible to include installation costs on rebate forms as an information-only item, meaning not strictly tied to incentives for program eligibility. But if you carried make model number through to tracking and required installation cost reporting in rebate forms and collected all that stuff, we would have a natural, comprehensive, low-cost, ongoing source for unit price data. You'd be able to track market shares by a variety of variables, and not to mention having installation costs, a large source for installation costs, pretty much in real time. The second kind of major recommendation we have is to standardize data development and analysis for measure cost estimation going forward. And we tried to break that out into as specifically as possible. What does it mean to standardize this stuff going forward? We recommend to leverage point-of-sales data as much as possible, wherever you can. It's a very rich data source. Third-party marketing firms are responsive to demand for this type of data, so we definitely recommend leveraging it as often as possible. We also recommend partnering with the supply chain actors for data collection for everything else. We felt that was a really tractable approach to get over the primary data access barriers that we typically face. The third one is to systematically use product compliance databases, and by that we mean those maintained by the DOE for regulatory requirements, or the California Energy Commission for Title 20, or the EPA's Energy Star eligible product database. That's really important for certain types of measures. It's really critical to get comparable capacity and performance ratings that are based on common testing procedures. It's a subtle point, but it's important because it can really mess up your analytics. We also recommend establishing hedonic pricing as the primary analytic framework. I think we've demonstrated how the flexibility that it provides right out of the gate. It's also remarkably transparent and reproducible, and what that really gets you, besides the value of transparency, is true comparability across studies and over time, and get us out of this apples and oranges world. And finally, we recommend a consistent use of artificial project bids. I didn't really spend much time on that, but we feel that that's a really effective method for both unit costs and installation costs for very large capital equipment. And those could also be repeated over time to enable longitudinal analysis. And the last one is we recommend performing kind of targeted market assessments as a way to inform the frequency and depth of future data collection for measure costs going forward. And this recommendation is very much related to, in past studies you see, oh well, the price will come down if you just do it more often. We haven't really seen that that's resulted in studies that are less lumpy, less expensive and less time consuming. By virtue of going through this, the study in California, we feel that if you really want to do a targeted update to a cost study, that you really have to do a market assessment up front. That tells you which estimates are still valid. Have there been changes in any standard practices that might impact incremental costs? Interactions with non-energy codes, especially air quality codes, has been something that influenced our work, and down and down. And by doing that, you really directly enable the scopes and the budgets of future cost studies and data collection to be truly targeted and optimized. And especially in jurisdictions that also have market transformation targets, market assessments provide other value besides informing measure cost data collection. And so we feel that that's a no regrets approach that could really enable more targeted and higher value cost study investments. So I'll leave it there. I think I've gone slightly over. I apologize to Mike Sherman. Questions at the end, and if you have to leave early, feel free to contact me or our project sponsors directly. So thank you.